Hey Psych230 students, just a quick video to review the muddy points from the correlation chapter. So if we look at those, let me go here. First thing we've got, Muddy's thing from this topic was trying to remember the degrees of freedom is n-2, not n-1. Had to go back to my work during the homework assignment. Yeah, I would definitely recommend for all of you, again, so think about it, if we got the final exam left, you are going to do calculations only on the correlation, the ANOVA, the correlation, and the chi-square. So those three statistics, I would have, a sheet of paper with all of the formulas in order that you would calculate them, maybe even an example worked out. So you can print something out from, that you've done yourself, from the slides, from the problem sets, what have you. Just so you make sure that you're using the right formulas for each statistic. So that's definitely what I would recommend. So if I taught that, when I teach this class in person, my students can bring cheat sheets, but they have to write out all the formulas, and so they have to make all those cheat sheets themselves. And I think that really helps them learn the material, but it also preps them for the exam. So I would definitely recommend that. And you only have the three statistics that you would probably want to do that for. So definitely check out that. And that should hopefully remind you that it's always n-2. Next one, Muddy's point for me is determining what a significant correlation, what the significant correlation with a high or low number is telling you and if they relate. Okay, so that's not super clear what the muddy part is. So I'm going to try to cover a couple things of what I'm guessing it's relating to. So first off, just to go back to the correlation itself is looking for whether two variables relate to each other, meaning that does how you score on one variable, whether you score high or low on it, does that seem to relate to how you score on another variable, whether you score high or low on it? So as a very simple example, is your height correlated to your weight? Yeah, probably. People who are taller, in other words, they score high on height, tend to be heavier. They tend to score high on weight. People who score low on height tend to score low on weight. Now, it's not a perfect correlation by all means, but it would probably be what we call seems to be some kind of relationship there, and it would be a positive one, meaning if I score high on one, I tend to score high on the other. If I score low on one, I tend to score low on the other. If I score in the middle on one, I tend to score in the middle on the other. So when you get a correlation, the number is telling you how strong that correlation is. Now, numbers will range from 0 to 1. A 0 correlation means no relationship. That these two variables are not related. So your phone number or your area code or your IQ is not related to your shoe size or to your weight or anything like that. Okay. In other words, you can have a high phone number or a high IQ or a high shoe size, and that's not related to your weight, right? So you could be high or low, who knows? So that would be closer to the 0 correlation. So closer to 0 means less of a relationship, closer to 1, more of a relationship. So a 1 is a perfect relationship. For every unit you go up in one, you go up 1 unit in the other. But a 0 relationship means nothing. So we're always looking at a correlation in terms of what's the size of that number between 0 and 1. And the closer it is to 1, the stronger it is. So that just means that the connection, the relationship is just a stronger one. It's closer, there's a closer link in a way. So one way, and then the other piece is that there's the sign, positive versus negative. So a positive correlation just simply means it's the direction of the relationship. So positive one means it's a direct relationship, higher in one, higher in the other, lower in one, lower in the other. But a negative relationship is the inverse. So what that means, if you're high on one, you're low on the other. But if you're low on the first one, then you're going to more likely be high on the next one. And so we're looking at these kind of relationships. So this top link here, the Our Psychologist one, is what I pulled up here as an example. So here's a really strong correlation. Notice how it's close to 1. It's a 0.93. So people who tend to score low on X, somewhere like whatever this is measuring, it's like somebody's like in the high 80s, low 90s, they tend to be low on Y. But if they tend to score high on X, they tend to be high on Y. And if they score in the middle on X, they tend to score in the middle on Y. And so that's a strong positive correlation. Now, I'm guessing height and weight might be something like this. It's a pretty strong correlation. But you can have people who are very tall who are really heavy, and some people who are really tall who are not so heavy. And you can have some people who are short who don't weigh so much, and some people who are short who weigh a good bit. But there is this kind of connection. Now, what I like about this visualization is it's also showing the shared variance. So if we're looking at height and weight, we can see that people vary in terms of their height, people vary in terms of the weight. Some people are tall or short, some people are heavy and light. But so let's say the dark circle is height and the light circle is weight. You can see that part of the variance in each is shared, meaning that these two variables are connected to each other. Because again, yeah, if you're going to be taller, there's more of you. And that's more likely to be that you're heavier. If you're shorter, there's less of you. So your weight should be less. But there are parts of weight that are not related to height. And there are parts of height that are not related to weight. And so the overlap is about, in this case, let's say with this correlation of 0.77, about 59% overlap. Now, technically what that is that's your R squared. If we were to take 0.77 and square it. So that's our R, we square it, and we get our percent variance explained. That's our R squared. And we can explain that about 59% of the variability in height, remember the dark blue is the height here, 59% of it, almost 60% of it, is connected to weight. Or you can flip it around, 59% of the weight is the light blue, is related to somebody's height. Now that means that there's 40% or 41% in this case that's due to other things like nutrition and environment and so on, genetics, etc. Okay? So now if I drag this down, you can start to see that those variables get more spread out. And so there's less and less overlap between these two variables. And when we get it down to about a 0 here, we will see that those variables don't seem to have anything to do with each other. Okay? And so what that's suggesting to us is that height, whatever we're measuring here is not related at all. And so, oops, I'm going the wrong direction here. There we go. So there's our 0 correlation. And you can see that once this catches up, and it's having a little bit of a hard time, is that these two don't share any variability. So whatever these two variables are, shoe size and IQ, not connected. They're not in any way related. So here's somebody with small shoe size, they could have high or low IQ. Here's people with medium shoe size, high or low IQ. People with high IQs, or big shoe size, high or low IQ. It doesn't seem to be related at all. In fact, IQ and shoe size share no variance at all. So if you squared 0, you get 0. All right, so that's what a correlation is going to tell you. So we can, let's say we get a correlation, let's say it's a negative 0.4 here. Negative 0.4, that tells us that these two variables are somewhat related. We would consider this a weak to moderate correlation. Now, so that's one thing, and it would be a weak to moderate negative correlation. So they might be related, they would seem to be related in a negative way. As one goes up, the other one goes down. And the R squared would be a 1.16, or 16% of the variance is shared. Now, that's one thing. So we can interpret the correlation just in terms of the strength of the relationship and what direction. But then we also, when we're doing a hypothesis test, we're trying to see, is this correlation statistically significant? Which means that then we're looking at this group of scores as a sample. We sampled a group of people. In this case, it looks like, 50 people maybe, 30, 40, I don't know how many we've gotten here. And they seem to have a negative 0.4 correlation. But when we're looking at statistical significance, we're saying, well, is this correlation of negative 0.4 just for the sample, or would it apply to the population? And if we find that it's statistically significant, we would say, yeah, it probably applies to the population. But if we found that it's not statistically significant, we would say it doesn't apply. And that's that issue of critical region. So we'd have to determine the critical region. We'd then look at is this negative 0.4 in the critical region or not? If it is, we're going to reject the null, which says that there's no correlation. And we're going to say, yeah, these two variables are probably negatively correlated. But if it's this negative 0.4 is not in the critical region, we would then have to conclude that this correlation is probably happening by chance. And so might not apply to the population, and thus we would say it's not significant. We would retain the null and we claim it's not a significant correlation. Okay, so you can have correlations that are not significant. So for the sample, yeah, they seem to be related, but then it's a question of would it generalize to the population? So that's hopefully answering that question. Issues with interpretation, hopefully I've answered a little bit of that, but the other piece that I think is really important is to then explore, well, okay, what does let's say we get a strong, and let's just make it positive because they're sometimes easier to work. Let's say we get a strong positive correlation of 0.81. We can see that that's a pretty large effect size. Almost 2/3 of the variability is shared. And that means that, you know, whatever we're measuring here, 66, almost 2/3 of that variability of people's scores on that measure is probably connected to this other variable. So when you get that, and let's say this ended up being a statistically significant correlation, it's got a pretty large or very large effect size, how do we interpret that? Now, the key here is all correlations tell you is that these two variables, whatever x and y are here, are connected. We don't know how they're connected. And this is why I would argue that the correlation is the most misinterpreted statistic out there. Because all it tells us, if it's statistically significant, is that there is a relationship. It doesn't explain how the relationship exists. So again, let's say we were looking at height and weight. So we have a correlation of 0.81 between height and weight. What does that mean? It means they're related. People who tend to be shorter tend to have lower weights. People who tend to be taller tend to have higher weights. That's really all it says. We don't know why. It's not that you can say height causes the differences in weight. It's not that you can say the weight causes the differences in height. You can't even say that because there might be a third variable. The problem is with the correlation is there's too many possible explanations for the result you're getting. And essentially it's, you know, I would argue in this class there's 4. The first is X could be causing Y. That is possible, but we can't conclude that because there's still 3 other options that we haven't talked about. So X could cause Y. Another possibility is Y could cause X. Whoops, sorry. Y could cause X. So that's our second one. Those 2 are what we call the directionality problem. We don't know if X causes Y or Y causes X most of the time. Now, you could maybe know that if you measured one first. So if it was like your high school GPA was X and your college GPA was Y, okay, then you would have to say the high school GPA came first, and so it might be able to cause. So we'd have to eliminate the possibility that college GPA caused the change in high school GPA. Couldn't do that because it came later. So we can at least eliminate that, but there's still 2 more issues. Okay, so you've got 3 issues. X could cause Y, Y could cause X, directionality problem. Third one is the third variable problem, meaning that the correlation between high school GPA and college GPA could be due to all sorts of other things. Could be due to socioeconomic status. Could be due to how many hours you work. Could be due to age. Could be due to who knows what. There's lots of possible variables that might be the reason why X and Y are connected. They're not connected directly to each other. They're connected through another variable. So that's that issue of shark attacks and ice cream eating. Sharks don't care at all about ice cream eating. So ice cream eating and shark attacks are correlated, but they're only correlated through a third variable, which is temperature. So people eat more ice cream when it's hot. Sharks are out, well, people are out more swimming when it's hot, and thus there's more likely to get attacked by a shark. So that's the third variable issue. So those are 3 explanations, and those are usually the ones we want to talk about. But in this class, we can also talk about the 4th one, which is simply that this correlation could be happening by chance. Okay, so those are our 4 possible explanations of what's going on. So in this example, there's one in here that I kind of think is a good one to talk about, is this one here, the correlation between churches and serious crimes. That looks like a nice, strong, positive correlation. Well, the problem is we can't say anything causal. All we can say is that the number of churches seems to be correlated with the number of serious crimes. One possible explanation is that churches cause crime. People are getting together when they're in church and planning crimes. Another possibility is crimes cause churches. Seems reasonable. That if there's more crimes in a city, people want some solace. They want a place to escape, and that's church. And so those churches become more popular. And so there's more churches. So one is churches cause crime, X causes Y, or the other is crime causes churches, Y causes X. The third variable issue is that why are these 2 variables related? Well, they're not directly related to each other at all. Maybe they're related through a third variable. This is probably the easiest and probably most likely explanation here, but we can't forget about the other ones. They're still possible, but the most likely explanation here is just size of the city. Bigger cities have more churches. Bigger cities have more crime because there's just more people. Smaller cities have less crime, less people, less churches. So that would be the third variable issue. And then the other question is, well, we only have a sample of 10 cities here. Would this correlation still exist if we resampled and added more people and did a different sample and so on? And that's that issue of statistical significance. Okay, so that's the interpreting correlations thing. So the phrase that you really want to remember is correlation does not mean causation. And I promise you that you're going to struggle with that the rest of your life. I teach statistics and I still struggle with it. It's too easy sometimes because our brains like to tell stories and we see one variable and another variable are correlated. Our brains want to interpret it as causal. They just will. It will make sense to our brain, and we'll just, if we're not working hard at it and trying to prevent ourselves from doing it, we will make that mistake. So just keep an eye out for that. Restriction of range got a little bit muddy. Not a big issue. Whoops, wrong page. The restriction of range just comes down to the fact that we might have a correlation, really strong correlation here between, in this case, school grade level and knowledge of geography, meaning that as we go, so 12th graders are much better at understanding and knowing some geography, where certain countries are, than first graders and third graders, right? Okay, so that might be a pretty clear, strong, positive correlation. But if we then just looked at grades 1, 2, and 3, so instead of looking at the whole thing here, we're only looking at this little chunk down here. And when you look at that, if you just look at that correlation, that's probably going to be a 0.2 correlation, maybe a 0.1 correlation. It's basically no correlation at all. So it would look like how far you are in school doesn't have any impact on your knowledge of geography. But the problem is that when you restrict the range like that, we don't have a lot of range of scores in terms of school grade. You might miss a correlation that actually exists. So if we expanded it out and get all these grades, then you start to see it's a pretty clear relationship. Another practical example of that is that a lot of schools use, or like for graduate schools, they use things like the LSAT for law school, MCAT for medical school, the GRE for graduate schools, these are placement exams. And these placement exams are there to predict how well you're going to do in graduate school. Well, if we take the people who are actually then get in, so let's say a school decides we're only going to let people into med school who have this score or higher. So only students who have that score or higher are accepted into this school. Once you're in that school, you've already selected a top scoring group. So imagine, just ignore the scale, the axes here, and just say, okay, if there was a strong correlation, well, now you're only looking at these people here. At that point, those MCAT scores aren't going to predict who's going to do better of those students who got let in, because at that point there really is no fine distinction. They're all high scorers, so they're all going to probably do pretty well, but who knows? There's not that strong correlation anymore. So that is a little bit more on restriction of range, but I would also just suggest try not to worry about that too much. And then the last one here, most confusing thing for me was interpreting correlation tables found in the literature, how asterisks represent level of significance, why they're only partially filled out. It's a sideways triangle. Also difference between R and R squared, both seem to measure correlation. So I'm going to answer that last one first. Yeah, the R and the R squared are so related to each other that they are very much both measuring it. It's just different ways of it. So the R is the strength and direction of the correlation. The R squared is the percent of variance explained. So it's more of an effect size. It is how, at a more tangible or practical level, because it's now about percent of variance, how much of the variance in one variable can be explained by the other variables. That's the effect size. Whereas the correlation itself is just how strong and in what direction is the correlation. Now, in terms of those tables, that's when we're talking about something like this. So what they mention here, and I think it's a great point, is that this is like this triangle. Okay, so there's a triangle of correlations here. And part of the question is, why isn't there the other triangle up here? There can be. And when there is, it's just going to repeat the same numbers. Because the correlation between 1 and 2, so here's 2, that's this row, and the correlation between 2 and 1 is a 0.11. Okay, so then if you wanted to fill it in up here, the correlation between 2 and 1 would be a 0.11. So it would end up being the same exact triangle here, just flipped. So it would just be flipped over, and you'd have a 0.11 here, a negative 0.02 here, a negative 0.14 here, and all of these are correlations of variable 1, money sent in trust game, with variable 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, which are all these variables here. So just flips. Sometimes you'll see that. It's sort of unnecessary, so that's why most of them will just do it once. And then sometimes what you're going to see where we have these dashes is sometimes you'll see numbers there, and that, just so you know, but this is something that's more from a research methods perspective, it is the reliability of that measure. So sometimes if you're looking at correlations between things that are measured using some kind of measurement device, it's how reliable that measure is. And that's an issue of psychometrics, and the more reliable tests are better. So that would give you a sense of visually how strong are the correlations, but also how good are the measures, and would all be in one table. Okay, so that's partly how you interpret it. And then in terms of the asterisks, it's typical that you're going to have one asterisk for a p less than 0.05 and two asterisks for a p less than 0.01. So the probability of getting these correlations, like this one here, that 0.15, negative 0.15, has two asterisks. So the probability of getting that, if there were no correlation between, in this case, gender and age, would be a 0.15. It's less than 0.01, so it's a less than a 1% chance of getting that just by chance. Whereas this one here, the 0.15 here, is the correlation between ethnicity and age. That's going to happen less than about 5% of the time. Okay, so they're ways to kind of look at which ones are significant. So if some researcher's looking at this, or somebody in this field is looking at this, they're going to go and look at where are the significant correlations, because those are the ones that are unlikely to be happening by chance. So they're probably real correlations at the population level, probably. And then they're going to look at the numbers. So those ones with the double asterisks are pretty significant. And then you can just look at the size of them. And again, that's a nice strong correlation between depth and money sent in this trust game. And then here's another pretty strong one here, a positive 0.38. Now here's a very strong one, neuroticism, but it's just not statistically significant. So a negative 0.9, it's really strong, but it just happens to be possible that it's due to chance. So that's how you would kind of try to read some of these. All right, so hopefully that helps with understanding correlation a little bit better.